Hello friends, in this video I am going to show you the linked list representation of the data structure Q. You are already familiar with the Q data structure, which is nothing but a FIFO data structure having a FIFO discipline, that is the first in first out discipline, where the elements are added from the rear and elements are deleted from the front. Whichever element comes at the beginning will be deleted at the beginning. So this is the discipline the Q follows. So we have explained Q as an array in our previous videos, but in this video I am going to describe and show the linked list representation of a Q. So suppose we are familiar with singly linked list. So if a singly linked list is used to implement the method or the methodology of the Q or the operations of the Q, then we can explain it in the light of the linked list. That is, we can explain the Q is in the light of the linked list. So let me just first draw a linked list and then show it and present it in the form of a Q to you. So suppose this is a linked list. Suppose this is a linked list. Suppose this is address 605, 705, 805, data 10, 20, 0, 705, 805 and null. And this is, normally this pointer is called the list pointer in the case of singly linked list representation, but in the Q as a linked list, we will take this to be the front and this to be the rear. That is, Q has two important parameters, just like stack has the important parameter top. Q has two pointer variables will be associated with the Q in this example, that will be front and rear. So front will be this one. Front points to the address location of the beginning of the Q. That is the node. That is the first node of the Q, and rear points to the last node in the sequence. So these are the two pointers, and this front has a value of 605 and rear has a value of 805. So this is a simple Q representation. For this Q representation to be defined in the way of user defined data structure, we use the structure definition for Q and as well as structure definition for the individual nodes which make up the Q. So first we have to write the structure definition of the individual nodes or the blocks, memory blocks in the Q, and after that we are going to define the structure of the Q data structure. So let's write the definition of the individual node of the Q. Suppose I can write like this: type def struct Q element here. There will be two parts, that is, each node I am taking as Q element. There are two parts, one data part, one address part. For data part we will write in data, and for the address part we will write struct Q element star next, and write Q element over here as well. So this is the type, this is the structure definition of the individual node which makes up the Q. And after that we are going to define the structure of the Q data structure like this: type def struct Q. What will be here? There will be two pointers, front and rear, which are of the data type, which points to the data type Q element. So there will be two pointers to Q element, one is front and one is rear. So let's write that Q element star front star rear and write it as Q. So these are the two structure definitions which are required to show you the operations, the add, addition and the deletion operations performed in the queue implemented as a linked list. So first we will discuss the addition operation. So the addition operation means any queue, any node which we want to be added to the queue will only be inserted at the rear position, because it is a queue, it is not a normal linked list, it is not an ordinary linked list so as to allow us to insert any node at any position, that is at the beginning or intermediate position or at the end. But in this case, since this is a special linked list which is representing the queue data structure, we can only add elements from the rear end, as we are going to maintain the FIFO discipline. So first in first out discipline. So if any node is to be added to this node, and that will become the rear node of the queue of the updated queue. So addition operation will be shown by an addition function, and I will just write the function and explain it to you what I have done and show you with the pictorial representation how the entire pointer operations take place. So let's write the addition function first and then explain it to you after writing that. Now we have written the code, and let me explain what I have written over here. I have written the add function, that is whenever a node is going to be inserted or added to the queue, it will be added from the rear end. So to handle that operation, we have written a code, and let me explain it to you. We have taken the return type to be void because nothing is to be returned from the function. Function name is add. There is a queue pointer, that is a pointer to the structure queue I have taken. That is a small q is nothing but a pointer to the structure queue, and we have taken an integer variable x, that is nothing but the data to be kept in the node to be inserted at the rear end of the queue. After that, we enter the function definition block and write queue element start t. So this is nothing but t is a pointer to the data type queue element, which we have shown previously. After that, we will allocate dynamically some amount of memory for a single node to be created, which node we are going to add to the end of the queue. So by writing this code, we dynamically allocate the memory. T is equal to queue element star malloc size of queue element. Then we put x, we assign x in the data part of the node pointed to by t pointer, like this. Suppose the t is created like this. Suppose it is created at a location of 905. It has two parts because it is a queue element type of node, and it is pointed to by t. T has a value 905. Suppose the user gives the value to be of x to be suppose 25. Then by this line t data is equal to x, we assign this 25 to t data, that is t data means 25 is to be assigned to this position, and t next is initially taken to be null, that is null pointer. So this is the position up to this. After that, we have to see whether there is an existing queue or if the queue is empty. Suppose if there are no nodes in the queue at the beginning, then we can also add the new node to the queue data structure, because in that case we can easily add, since there is that will not be an impediment or an obstacle in the addition operation if there is no existing linked list representation of queue at the beginning, because in that case we will add this new node as the front node, as well as that node will become the rear node. In that case, we have dealt with that case in this section of code where we have written if queue front equals null. If queue front equals null means, suppose queue front is this one and it points to null. So there is no existing queue now, And if we go to add this one to this existing condition or to this existing situation, we will have to do some necessary pointer operations for that specific case. So we have done that. If q front equals null, that is the q is empty at the beginning, then q front is equal to t, q rear is equal to t. Q front is equal to t and q rear is equal to t. That is, in that case, this q front will point to nothing but this one, that is 905. That is 25 will be the data, here it is null, and this is the t, and q front will be pointing to the same location as t points to, and then q rear also points to that same position, because this is the only node in the queue now after the addition of the new node. Then this only node is the node which becomes the front node as well as the rear node. So in order to deal with that situation, we have done this, we have written this code, and after doing that we have written a return statement and go out of the function body. If it is a generalized case, if this is not this sort of case, if this is not this sort of case, then that can be a case which is just depicted on the board, that is having 3 nodes or 2 nodes or 1 node at least. Then we have to add this node to the end of this list. What to do for that? There are 2 pointer operations. Please let me show you that pointer operation what we have done. Suppose we are not dealing with this case, please forget this case and concentrate on this case. So if we want to add this 905 memory location to this 805 memory location, what we have to do? This is the q rear, then q rear's next part is now null, and this next part, in order to be linked to this 905, should be having the value 905. So we have done that only. Q rear next is equal to t, that is q rear next is equal to 905. By this, we are establishing a link between this node and this node. Understood? And after that, we update the rear pointer. Suppose after the addition of the new node, the q becomes larger, and this will be now the rear node of the q data structure. So the rear doesn't point to this 805 memory location. Now the rear will point to which one? Rear will point to this 905 memory location. So this q rear is equal to t, means q rear is equal to 905. So this is the addition operation of the queue in the queue as a linked list. And now we are going to write the deletion function and show it to you. Let's write the code of the deletion function and get back to you. So let's explain the code of the delete function. We have written a function for the deletion operation, that is the delete function, having a return type int. Why we have taken a return type over here and not in that case? Because there was nothing to be returned in the previous add function, because everything would have been a successful operation, because we could have added a node to the queue if the queue was empty, or there is no queue full condition, so we could have added the new node to any position in the existing data structure. So that was not a case where there can be a failure operation. So we didn't have any return type, so we kept the return type to be void in that case. But in this case, since we are dealing with the delete operation, we can encounter a situation where the queue is originally empty. So in that condition, we will not be able to delete any node from the empty queue. So in order to deal with that situation, we can encounter a situation which is a failure operation, which can prove to be a failure operation, and for that case we need to return 0 from the function, and in the case of a successful operation we are going to return 1. So for that we have taken this return type to be int, function name is delete. We have taken a pointer to q data structure small q, q star q, and an integer pointer star a to hold the data item from the deleted node from the queue. From where it will be deleted? The node will be deleted from the front of the queue, because we are going to maintain the FIFO discipline, because we are dealing with queue data structures. So we are going to delete the node from the front position of the queue. So the first node of the entire sequence of the queue will be deleted in the process of deletion. So now we have written queue element start t. We have taken a pointer t, which is a pointer to the queue element type of data type, queue element type of structure. If queue front equals null, this means if queue front equals null means this is the empty condition testing. That is, if the queue is empty, then obviously queue front, if the queue is empty, then obviously the queue front will be equal to null. In that case, we are not going to delete, or we will be unable to delete any node from that empty queue. For dealing with that situation, I have written this part of this code. To deal with the empty condition, we have written this part of the code, and that is written like this: printf queue is empty if this condition holds. We will print a message, and a is equal to null. Nothing is to be returned. Nothing is to be assigned to the pointer variable a. Nothing is to be assigned to the pointer variable a in that case. So a is equal to null, and we have returned 0 from the function, and get out of the function and skip this entire portion, because we are encountering a situation which leads to a failure operation. So this is the part for that empty condition. For the general part, we again come back to this portion of the code, the remaining part of the code, and we need to forget this part and get on with this part. So this part starts from this line: t is equal to q front. So this, what I have done, t is equal to q front. So suppose this is the queue having 4 nodes, 605, 705, 805, 905, of which this is the front and this is the rear. This is the rear node, and we have to delete the first node of the sequence for the deletion operation to be executed. So t is equal to q front means we take this t pointer to point to the same location as q front points to, that is t points to 605 memory location. So t and front are the same position. Now what we have done, q front is equal to q front next. We have updated the q front to point to the next node in the sequence, that is to the second node in the sequence. That is, q front doesn't point to this one 605, but now it points to, q front points to which node? The next node in the sequence. That is, q front is equal to q front next means q front is equal to q front next means 705. So q front is equal to 705. So q front is equal to 705 means q front points to this 705 memory location. 705 q front is equal to 705 means that q front points to 705 memory location. So that is correct. And after that we have written like this: star a is equal to t data. Suppose, what is t data? T data means this 10, and that 10 is to be assigned to this star a, that is the value at the address, value at the pointer a, value at the address a. So this is the value which we will store in star a and can print if it is required, and we keep this t data in the star a and come to this portion. This is an interesting part. See this, these two lines are very important and very interesting. See this: if q rear is equal to t, if q rear equals t, q rear is equal to null. That means if the queue would have been a queue containing only one node, that is this one. Suppose front is here, suppose rear is also here, data will be something like, you can imagine, -10, memory location, say suppose it is 777, this has a null pointer, and if the queue is only this part, a standalone node represents the entire queue, then in that case we have to make some necessary changes, for which I have written these two lines. If q rear is equals t, that is, by this logic we have taken t is equal to q front. So t is equal to q front means t points to this 777. Now t front and rear all are at the same position. After performing this operation, q front is equal to q front next, Q front becomes how much? Q front becomes null. See this, Q front next means null. So Q front becomes null. Now T front doesn't remain here. T and rear are at this position pointing to 777, and after that we have to do this pointer change. If Q rear equals T, see this, Q rear equals T condition, this condition holds. Q rear is pointing to the same location as T points to. So in this situation, this condition holds, and we have to write like this: Q rear equal to null. That means we need to make the Q now empty after deletion of this solitary node. So in that case, Q front points to null by this operation, and we need to also make the Q rear point to null as well in that case. So in order to deal with that particular case, that particular special case where there is a solitary node which is to be deleted by the deletion operation, we have written this code: Q rear equals to null. That is, after the deletion of this node, Q front and Q rear both will be pointing to null. So this condition is dealt with in this portion of the code. After that, we again come to the generalized section like this one, like this case containing 4 nodes. T next is equal to null. T next means this one. T next becomes null. It is delinked. And now we have written free T. We have freed T and returned the memory which was occupied by the memory location 605 to the memory pool. And then, since it is a successful operation, I have returned 1, and that is the end of the function. If you have any doubts and queries pertaining to this entire section which I have explained to you, you can well post your doubts and queries into the comment section below so that I can address them. Thanks for watching this video.